Okay. Yeah, so let's take a look at what these polar coordinates are with a little kind of example here. So let me share this picture. Okay, here's the DVC campus map. Okay. We are in the math building. So we are right, this MA, can you guys see that? Yeah, okay. So we're right here. We're right here, and let's say your friend is in the business and world languages building. They're over here. Okay. Let's say this grid, when you look at the campus map, right? They usually have it by letters on the right and numbers on the bottom. So it's kind of like a point, like an X and Y point. So to locate where the math building would be, you would locate the number that it's under, and then you would locate the letter that it's under. You would need those two coordinates. Is that how, right? Usually how you've been using a map? And so what that's going to be now called rectangular coordinates, okay? Because you move in a rectangular way, meaning you move up and down vertically or horizontally left and right, okay? And so if I wanted to walk to my friend, let me move this down here. If I wanted to move to my friend, I would take a path. Let's say I can only move sideways. I would go up. That would be like the Y distance. And then I would go left. That would be like the X distance, right? So this coordinate system is completely different from that. And it talks about, uses angles and it uses length. And here's the idea of it. So let's say I have an arrow here. I'm going to start the arrow or array. It's also called array. I'm going to start right where I'm at. We're in the math building, right? And just like you guys did with trig on the unit circle, I'm going to start on the positive and the direction that starts at the left. Wait, on the right. And what we're going to do is we're going to rotate by an angle theta, just the way you guys did in the unit circle. And I'm going to rotate this arrow all the way till it starts pointing where my friend's at. So I rotate by a certain angle, boom, my friend's right there. Have I located how far they are from me though? No, so then I stretch my ray, and then my ray will tell me the distance between me and my friend, okay? So in this case, I'm not thinking about how far are they vertically and horizontally to get there. I'm thinking about what angle can I use to point where they're located relative to me? And then how far do I stretch this ray to see how far they are? So I'm using angle to rotate towards they're at, and then length to stretch to how far they are from me. Yeah, question. It's kind of like that, but we don't depend on the I guess the short sides, which is normally the horizontal and the vertical. In this case, we just care about the angle part. Yeah.
Does this check on like the side and the side?
Side angle. No. Like geometry, right?
Or just solving for sides.
What's the word I'm looking for? Spoiler, trig is involved. So yes, eventually it'll touch up on that. Okay, that's where this section comes after the trig part. But now let's say my friend was located by the lake. They're over here by the lake. So they would tell me, okay, I would rotate by a certain angle and then stretch it far enough so that I can see the distance that my friend is. That's kind of the gist of polar coordinates. Okay, so let's see now what it'll look like in action. Any questions? Okay. It's going to get tricky. Whoops, it's going to get tricky because as we saw with angles, I can say I rotated by the small angle here, the small acute angle. What's that? Maybe like 30 degrees. Okay. Or I can do one full rotation and then rotate there as well. There's multiple angles that can describe the rotation needed to point in that direction. Because they're all coterminal. That's exactly right. Yeah. And you can also do negative as well. Not with the coordinates, no. As long as if you're in the, if you rotate negative, you just have to make sure that you write a negative angle, and you'll see what I mean. Yeah. Okay, guys, so let's take a look. Let's see exactly what this is gonna look like. All right, so let's see, section 10.6. Polar coordinates. Polar. What do we call it? Polar coordinates. Points. And equation. All right. So up to now, we've plotted points x comma y on a rectangular coordinate system. Has many names. Euclidean plane, XY plane, there's a lot of names that you've heard for it. Right, there's a point located right here with coordinates x and y. We've learned that this distance, this vertical distance here, and this horizontal distance give us that direction, right? This is located right below whatever this x value is, and this is located to the side of whatever that y coordinate is. Okay. And we call this guy here the x-axis, and we've been calling this one the y-axis. Nothing new. Yeah. And so, like I said, this requires a horizontal and vertical. Not a, sorry, this requires horizontal and vertical directions. And so what we're going to do today is kind of what we're showing you there on the map. So today, what we're going to do is learn how to plot points using rotation through an angle theta. So we're going to call theta that rotation and length r. And so think of being on the the rectangular coordinate system here with your x and y axis, but we're going to have different names for them. Let me slow down here so you can write that down. And so let's say we have a point right here. Okay. And remember how I said in the map, we started that arrow by being in the math building. Okay. Here, this will always start with a point from the origin. You'll always go off the origin. Okay. And we're going to figure out how far this point is from the origin. Okay. And so here's kind of the way it goes, the way I was showing you guys here on the computer. You're going to start just the way you did with trig, rotating theta on the positive x-axis. But now this axis here going towards the right, they're going to call that the polar axis. You still start with your theta at 0 here. And then just as we did, you're going to rotate that ray by a certain angle so that it points towards that point. And then you're gonna stretch that ray so that it stretches up towards that point. So you're gonna end up with a ray shooting from here, ending right there. Okay? So you got your ray starts at angle 0, and then it rotates by a certain angle theta, just as we've been doing it. And the length of this ray is what we're gonna call r. That's the length of the ray. How far this point is from the origin. Okay? And then now, that point, instead of calling it x comma y, is gonna have the coordinates of the angle and how far it is. And we're gonna call that r comma theta. That's the two pieces of information you need. Tell me how far I am from the origin and the angle needed to get me to point towards it. Okay? So whoops, I can't spell the angle theta and length r are called the polar coordinates of the point. Polar coordinates of the point r theta. Oh, and I forgot to say here, for the XY point that we've been using, the X and Y are called, sorry about that, forget that. The X and Y are called the rectangular coordinates. Rectangular coordinates of the point X comma Y. So when you see rectangular coordinates, it's talking about x comma y. When you see polar coordinates, it's talking about r comma theta. Both different ways, both different systems to show you the location of a point, but in a very different way. Okay? All right, let's play with them for a little bit. Kind of get the feel for them. So let's plot the points. And I'm going to write them in polar coordinates. We're going to call the point A 2 pi over 4. We're going to call the point B 3 negative 5 pi over 6. And we're going to call the point C negative 4 3 pi over 4. Okay. So let me give you an idea. Let me first revisit how you learned this, even though I know you already know, but let me just explain that part so that you can see how you're going to do this. Okay. So if I was to erase all this stuff, you have your, let's say it's like this. We've labeled our X and Y axis like this, right? And then you guys had a grid. Think of a grid that you had here. You had a grid. Let me see if I can draw it. You had a grid that you were imagining in your head, like this. And then the point was located right here. That point was the intersection of the X value here and then the Y value there. So wherever those two coordinates intersected, that's where you were plotting your point. So the way we're going to do this, theta talks about rotation. So think of a circle, right? And R talks about how far off that circle are you. So think of the radius of this. Okay. So if I want to start plotting a polar point, think of R, if R is 1, I have a circle of radius 1, a circle radius 2, a circle radius 4, sorry, 3, circle radius 4. And so think of me having this circle that's kind of going around, where this is always 1 unit away from the origin. This one is a bigger circle going around that is always 2 units away from the origin. This one's 3. So that all the points on this circle are 3 units away from the origin. And then this one's 4. How are my circles coming in? All right, they're decent. Okay. So the R is going to give me how far I am from the origin, right? So this point is how many units away from the origin? It's 2 units away from the origin. So it's going to have to lie in the circle of radius 2. But now I need to know where on the circle it lies. And that's where the angle is going to help at pi over 4. So my ray is going to stretch up. Oh, hell yeah, perfect. My ray is going to stretch here at 2 units, but then I have to rotate my ray to pi over 4, right? So I have to now rotate it to this angle direction, which is pi over 4. And so just the way this point is located in the intersection of the x value and the y value, this point A is going to be located where the circle of radius 2 intersects this direction of angle pi over 4.
But shouldn't it only go towards like 2 or stop at 2?
Say it again?
Yeah, it stops at 2.
It stops right at 2. Yeah, so that point is located right there. You don't actually draw the ray. You don't draw the little arrow. It's just a point. So right here is point A. Okay. So draw this real quick on your notes. Just this one time. Yeah.
Might be equivalent to, I don't know, just my soundtrack, but like just adding pi over 4 to 2 or.
You're not adding
that
them.
concept, or basically moving to.
You can think of it in 2 different ways. Yeah, you can think of starting with length 2, right? So you're saying, okay, I know I'm 2 units away. So I'm going to start here, but then I have to rotate it at this angle, which moves me here.
Okay, so then the second one would be starting from 3, because there were 3, with 3.
3 units away from the origin.
Origin and rotate to
Negative 5 pi over 6. Exactly. So for point B, we're 3 units away from the origin, right? Actually, let me write all these little things here, guys, so you can see it. Theta here is pi over 4. Here, R is equal to 3, and theta is equal to negative 5 pi over 6. So what circle does this have to lie on?
3.
Circle radius 3, because it has to be 3 units away from the origin. But now I have to rotate by negative 5 pi over 6.
So you would go that way.
I'd go this way, and then you'd have to use your knowledge of where 5 pi over 6 is located.
Okay.
Okay, so here's negative pi over 6, negative 2 pi over 6, negative 3 pi over 6, negative 4 pi over 6, negative 5 pi over 6. So circle radius 3, and then right there. Here is negative 5 pi over 6 rotation. So this is where point B is at. Right. You can see that? Okay. If I was to rotate this by a positive angle, and you also wanted to land right here, what angle would that be for it to be positive and end up exactly? It would be 7 pi over 6. Exactly. So this point B can also be written like this: 3, 7 pi over 6.
Oh.
Yeah.
Because it's still the same.
It still gives you the
just a
same.
positive.
It still takes you to the same ending point.
Okay,
Yeah. So what's different about polar coordinates and rectangular coordinates is that rectangular coordinates are unique. Only one point can give me that point. One X and one Y can give me that point. But for polar coordinates, they're not unique. I can have hella different points. Because I can do negative 5 pi over 6, 7 pi over 6, but I can do like bigger rotations, right? So there's infinite number of coordinates that you can use to give you the same point. Is that okay?
Yeah.
Okay, and then it gets even weirder with the negatives. So this says that r is -4 and theta is 3 pi over 4. So this time let's start with the angle. Positive 3 pi over 4. This is positive 1 pi over 4. Positive 2 pi over 4, which is pi over 2. And then 3 pi over 4 is located right here. If this was positive 4, then it would be located at the circle of radius 4 that rotates to positive pi over 3, and then the point would be right here, right?
this is just
So what do you
not-
think it's negative is gonna do?
It's gonna switch it, like,
The opposite.
I heard
Opposite.
mirror, opposite, and switching it. I think those are all around the same thing. Yeah. So what you do is your ray rotates 3 pi over 4, but instead of shooting towards the direction that it's pointing, it shoots in the opposite direction. So instead of being the point shooting here, it goes 4 units backwards. So it's actually going to be mirroring it, as you guys said. So instead of going this way, it's going to point it completely opposite in the opposite direction from the origin. So it'll be located right here. Okay. What angle is this? What negative angle is this?
3 pi over 4. Or no.
Negative.
Pi-
Negative pi over 4, right? This is negative pi over 4. So what's another way I could write this if I want the angle to be negative pi over 4?
Or
4, -5,
Positive 4 or negative 4?
positive.
Positive 4, because now I rotate towards negative pi over 4 and my ray does point that way. So then R would have to be a positive 4. Tricky, right?
Yeah.
Tricky. Yeah,
For us to graph it, is like, since it's weird with circles, do we just need the general area, right? Like,
correct, yeah, because here this is pretty like simple, simpler to kind of see that. But yeah, here, what you're gonna do, and I'm gonna give you guys a sheet of paper. You usually, instead of using a rectangular coordinate system, you use a polar coordinate grid, which is basically this. And you can't see it from here, but it's the XY axes, right? But instead there's circles going around. And then there's these rays that are giving you the angle direction. Okay. So let me show you a couple more things. I'll put this back up. Okay,
is there a way to go directly from your rectangular like coordinates to the polar?
that's the second part. Yeah, I like it. All right. All right, guys, so let me show you. So on Desmos, if you want to use Desmos, right now we have a rectangular grid. So if I go to settings, see this guy right here? This is going to give me a polar grid. Okay. And so the point A that we plotted had coordinates 2, pi over 4. Right here. Wait, is it reading it? Oh, damn, it's not reading it as it's reading it as an XY point. But it would be right here. It would be at 2, and then you guys can't see it, huh? Let me see if I can make it darker. Hold on. Can you guys see the, there we go, there we go. So it'd be 2, and then see how here's pi over 6? The one in between is pi over 4, and then 3, so that point should be right here, the way we plotted it. Okay? And then we did 4, -4, 3 pi over 4. If you would rotate 3 pi over 4 the way we did, but instead of shooting out 1, 2, 3, 4 this way, you go backwards. 1, 2, 3, 4. That's the last point that we did. Okay. Questions?
Now, those circles are a lot bigger. Does that mean we would actually put it all?
Oh, but yeah, you're right. I measured that wrong. Let me go like this. There we go. Okay, let's do it again. So 3 pi over 4 was here. And then now you would go 1, 2, 3, 4 backwards. There we go. Sorry.
No.
All right. So I have, I'm gonna pass this out. Let me explain it real quick. So you have 3 points, A, B, and C. And for each point, what you're gonna do for point A, you're gonna write it 4 different ways. So that in this one here, would it be better if I project it? So you guys can see it in the back? Yeah, okay, hold on. Technology. All right, give me 1 second. Let me just open it up. I'm gonna pass this worksheet out. Let me explain it. Okay, so what you're gonna do is there's 3 points, right? A, B, C. And what you would do is you're gonna write point A so that in this one, the R is positive and the theta is positive. Here, you're gonna do it so that the R is positive, but the theta is negative, and so on. Does that make sense?
Yeah.
Okay. Sure?
Mhm.
All right, so let's try it out. So let me pass these out. These are big gap between. You guys can see the lines, right?
Yeah.
All right, guys, so let me have you guys, just check in with your groups that they're doing these points. I'll go around, help you out.
Yeah, basically, I'm thinking, okay, so. I'm gonna just number this out.
Like that graph was, because it's not 5.
Yeah, so the grids, the circles here are, radius 1, radius 2, radius 3, radius 4, radius 5.
It was
I
five.
don't know, this is, yeah, this-
It goes 1, 2, 3, 4, 5.
Oh, the.
The last one,
Would be
biggest
the
one.
five.
Yeah,
Okay.
the last, the biggest one.
Alright, I just did that, because you know how he's doing it over there, like. You know how the circles, the. Like you see, yeah, like the circle, basically doing it like that, like it's number. that.
Well. So.
it-
Term of 4 is then B, and it just shoots the forwards. That's not the way. All these actually end up.
Oh, okay, so it should be 6, 7, 5.
I guess, I thought you were saying, translate A, so
There it is, right?
All the points that you write for row A, all those points that you write have to end up at what point A is located. Okay? Yeah, you have to end up where point A is located.
So then, if it's. The positive is probably for. Then the negative would be. This way, right?
Want to use your unit circle to help you?
That's where we're gonna use.
So both are- this is negative.
It means, what angle makes you go?
No, no.
forward?
Is that- this is not-
Right, negative, instead of, like, it's part of the first one, like, you're going. So what would the angle be if you like all the way up, so like.
So like, you see how for point B, the R is positive, but the theta was negative?
I don't know. Some put there, but yeah. it's for-
Oh.
These right here.
I look in memorized
Square.
it. Look in
And in
memorized it.
here, the R is positive and the theta is positive. Yeah, so it does, this doesn't correspond to quadrants.
Okay.
Yeah. But both of these points, they both end up here. They have to always end up at that point.
I see what you're saying.
Yeah. So you guys are doing that? Let me pass that to the one up. Yeah, the whole bunch of them. You're welcome. I'll bring her people. You want her to feel the detail.
So then, this one would just be -4. We will find out from one of them.
No,
No?
no, because I remember like that would mean that the ones,
Okay.
it'll be. But I don't know. I think so understand, you know what? If it was negative one now, I think you need to find here and that's maybe we do so here, so then when you were able to do. Yeah, it would be an overboard, but the angle would be. Yeah, that's what I think. You get one, yeah, like since then, before we just first one there, somebody.
I'm gonna post solutions on Canvas that are possible solutions, but you might have something different.
I haven't done this. This is a 7, but oh, because- oh, we're gonna have that. Sorry. That's fine. But I'm not it.
Well, yeah, this 6 is.
Mhm.
But this.
Mm. So then I'm thinking,
Oh, yeah. Right. You know, so
mhm,
yeah, so what. But you need to-
like yours,
Mhm.
right? Like, are you saying like exactly like this? Yeah, so this is 7
Mhm.
but this is 7. I was like,
No, yeah, it would change the construction.
this.
And it's still with things.
Mhm. The speed is 7 with it.
It's gonna be the same, yes.
So if it's so negative, mirroring Negative 6. So it's right here. But then it's gonna be measured. Confidence. 5 was. I thought it's the last.
All right, ignore my solutions, they're wrong. I missed the grid completely and
Yeah, you know.
I'll do it again.
When like.
I'm just gonna remove
When
them.
it's -4, it means that.
Yes, you're correct.
So you need to find what is this for?
It's just the R, okay.
Because you want to get that into here, so when it goes negative and then the mirrors, it'll be. So you need to figure out what's that can go down. Yeah.
4.
Why for A, where do you reach 7.5 before?
Oh, wait, you were just talking in general, right?
Yeah, so.
But I
A
assume you
A
were
is prime.
before, yeah, and then if you mirror it, it will be like.
Right.
Yeah. Okay.
There is the point there.
Yeah.
No.
Because the negative means that the rate is there, but you need to go negative before to get back there.
An example for when they're.
Yeah. Well, got settled on fire, it's fire, it's because of the memory. Yeah. Okay, so. Remember in the place when I explained this to you, you know, this involved.
This one?
Let's do A. 'Cause it's so fast. No, we could do it since it's.
Four, right? And then. Answer, so we're gonna just have there. Where,
Instead of going this way, we go.
so like when it rotates towards the negative sign, where does it end? Start.
Yeah, so like. when you go against it, It's fire.
Yeah.
But what is it? When you go like that. This one. Okay, let's recap this one. So like, we're trying to find the angle directly.
Yeah.
So it's the same, instead of finding what's this angle starting from this side, what's this angle starting from this side? So that's where both of them are.
Yes. So this one will be when it's Wednesday and we're starting from this.
Let's say like this one. Instead of finding, okay, so it's -4 and it's 5.4 to get here, instead we find them. And that's fine. So 5.3 doesn't hit different. It means this. Like, this would be 5.3 would actually be
Yeah.
And then.
Um,
Oh, okay.
Yeah, I think this is so backward.
No, not quite. So like, you could even think about it as distance, right? Like, this is 5/6. This is like the less than circle.
Yeah.
And like this distance, going down, is 5.
Yeah.
So like, this distance will never be able to go all the way.
Yeah, my thoughts were.
So if you were looking for, okay, so it's at 5/4. Cross would be. It's five.
Keep going.
Yeah, you got it.
Go back to this.
Yeah, so you're going like, I'm not sure what the best way to put it, but like, you're not going a full time, right?
On the auto part of the.
Half this, you're going in between half the time. Well, you could write the same way over here. You're not going half, you're not going. You're going. So the distance here. Yeah, that was it. But the whole thing,
Instead of me walking this road.
let me.
To not know any.
Because
To make me walk backwards.
This graph that makes it even more. Just when you're looking at negative, like you should imagine the graph. When you're looking at negatives. You should imagine a graph reversed where like.
So this tells me.
They want to redo the whole thing.
Walk backwards and walk back.
And you'll see that eventually.
All right, guys, we're gonna move on. We're gonna move on.
We done with that section?
You always ask that question, wishful thinking, I love it, I love it. We are not. We're now gonna answer your question. No, now we're gonna do the conversion.
Is that the last of it?
And then we're gonna convert equations,
Oh.
and then you are gonna wish it was the last, of it, yes. And then, yes, it'll be the last.
You're broke.
Okay, guys, we're gonna move on. We're gonna move on. So, as I was explaining to some groups, think of the theta, like let's say this is, let's say this is the zero, right? Zero angle. The theta, and imagine me as a person. I have a direction, right? I'm always looking this way. I don't look behind my head, right? So the theta is gonna tell me where to rotate. And then the R, if it's positive, tells me to walk in the direction that I'm looking at. Versus if it's negative, it's gonna ask me to walk backwards in the direction that I'm looking. So that's kind of the feel of what the R is doing. Walk towards the direction you ended up looking at, or walk backwards. Okay? Okay, so now, Bobby earlier asked, can we find a way to convert a polar coordinate? And let's say I look at this point A, and I want to say, well, what are the rectangular coordinates for A? Like, how far, what's the X coordinate and what's the Y coordinate? How would we find that? Okay, and this is where the trig is going to come in. So converting polar and rectangular points. Let me double check it's recording. Okay. Okay, so here's the question. Start with this one first. So given a point r comma theta in polar coordinates, how do we convert that into an xy point? And then similarly, if I have an xy point, how do I convert it to a polar point? And the answer is something that you really, really like. Trig function.
I know that.
You know those? We were testing it on them on Monday. Okay, and so here's kind of the idea behind this here. Let's start with what we know, x, y here. And we have this point. Give it a different color. We have this point. That we can write either now as x comma y. Or you can write in polar coordinates as r comma theta. Okay. We know for x comma y that it's located at this x value and it's located at this y value. Okay. But now we also know from our polar coordinates that there's a ray that shoots towards it that rotated by some angle theta, and that ray has length r. We also know that. Okay. So what we're gonna do, because we want to use trig, is we're gonna make a right triangle. Okay, and we're gonna do that by shooting down this imaginary line here that creates a 90-degree angle with the x-axis. And so notice that this created this right triangle. I'm gonna make it bigger though. Like this. Where theta is located here, that's the angle that we rotated. How long is the hypotenuse of this triangle? It's gonna be r units away, right? Whatever that r value is. How far is this bottom side here?
Okay.
It's x units away. You see that? Okay. How high is it? It's whatever that y value is. So it's y units away. And so then here we bring in our SOHCAHTOA to help us out. Okay. What's cosine? What's cosine of theta?
Adjacent on my hypotenuse.
Adjacent over hypotenuse. And what's sine of theta? Opposite over hypotenuse. So then what we do is we want to solve for x and we want to solve for y. Multiply by, if I want to get x by itself, multiply both sides by r, multiply both sides by r. And so this, we can rewrite it as x, this cancels. So I'm going to rewrite it as x equals r cosine theta. And then here the r's cancel. So now the y coordinate is going to be given by r times sine of theta. Have you guys ever seen that right there? Or in the previous class, maybe not.
The left part.
So we're going to use this guy right here to convert from polar coordinates to rectangular coordinates. And how are we going to do that? Well, look, this is a polar point, right? You know the r value, you know the theta value. So this tells me that the x coordinate has to be that r value times cosine of that angle. And that'll give you the x coordinate. And the same thing with the y. So given the r's and the thetas, you plug them in here and it'll spit out what x and y are. Right? But now what if we have the opposite? What if we have the x coordinates and I want to find the r's and the thetas? Okay. See, it'll be a little trickier here to use this, right? Because if I'm given x, I have two unknowns here, right?
Just x divided by cosine.
But you don't know the theta.
Yeah.
Right? So we're going to use a little more trig. Okay? We're going to use tangent. So if I want to use tangent, what's tangent of theta? Opposite over adjacent. So look, if I know my X and my Y, I plug them in here and that'll help me find my theta. And then I want to use the fact that this is a right triangle, so I can use a particular theorem. Pythagorean theorem, right? So it's going to be the sides, the square of the sides equals the hypotenuse squared. And so notice, given my X and a Y, I have an equation with just the unknown theta, so you'll be able to use that. I plug into my X coordinate, I plug in my Y coordinate, and it'll give me my part.
Can you remove the tan to get just the angle?
Yeah, I'm gonna talk about that a little bit. So you're gonna convert, this will help you convert from X, Y's rectangular to your polar coordinates. So, it's always in the way. I don't know erase this, but I have to space. Okay, so now, yeah, Bobby was asking, so how do you get rid of the tangent so that you can get theta? Okay. Well, remember how when you guys were solving trig equations, if I had like tan of theta equals 1 or something, you guys use the unit circle to figure out the theta? That's if you needed all the thetas, or all the thetas from 0 to 2 pi. Okay, but you don't need multiple thetas, you just need one theta. As long as you have one theta, it'll help you out. So in this case, you could use inverse tangent to help. Apply inverse tangent to both sides, and then if you use inverse tangent, you'll get that theta is tan inverse of y over x. But if you use inverse tangent, there was a restriction on the angles that you can consider for inverse tangent. You guys remember the restriction? It was, but theta had to be, but theta is within negative pi over 2 and pi over 2, not including the things, or negative 90 degrees to positive. So as you guys saw, right, like right now that you were doing on the worksheet, if I use an angle from negative 90 to positive 90, what quadrants does that cover? Only 1 and 4, but what if you have a point that's located somewhere over here?
So then you can do
So what we just did.
Exactly, then you use a negative r. You have to consider, do I want my r positive or do I want my r negative? We'll do examples. Okay, but yeah, it's starting to get nasty.
Oh, my goodness.
Woo!
Abort mission.
Abort mission. Okay, so let's take a look. Let's play with some more familiar points. So let's convert to rectangular points. So this time we're going to let the point A be have polar coordinates 1 and 2 pi over 3. B will have 1 and pi over 4. And then C will be negative 2 and pi over 4 as well. Yeah. Okay. So for point A, this is in polar coordinates, this is my r, and this is my theta, okay? So which one do we want to, which conversion equation do we want to use? The second one or the first one? The first one, because you're given the r's and the thetas, right? So to find my x, I'm going to do r cosine theta, but then I just plug in the r, which is 1, times cosine of 2 pi over 3. So now you have to use all the stuff you learned in the previous sections. So then you would say, what's cosine of pi over 3? 2 pi over 3? What is it? Negative. Negative 1/2. So then that x coordinate would be negative 1/2. That's going to be the x coordinate of that point. Okay. Now let's do the y coordinate. Same thing, but now it's sine. So it'll be 1 times sine of the same angle. What's sine of 2 pi over 3? Root 3 over 2. Look at that. Love it. Good job. So that's going to be root 3 over 2 for y. So then my final rectangular point will have coordinates negative 1/2 and root 3 over 2, which are the points from the unit circle. Hey. Okay. Because on the unit circle, you've rotated theta by 2 pi over 3. You rotated theta by 2 pi over 3, and r is 1 because you're on the unit circle, right? So that's why those are the coordinates. Okay. Yeah, question.
Was there a point where it's necessary to like use the calculator instead of the
Yeah.
circle?
Yeah, if the angle is not a special angle.
Okay.
Yeah, if it's not a special angle. All right. Let's see here. So here I'm gonna go a little faster. So x is gonna be r is still 1, theta now is pi over 4. So it's gonna be 1 times cosine pi over 4. What's cosine of pi over 4? Root 2 over 2 times 1. So it's root 2 over 2. And y, surprisingly, or not surprisingly actually, is gonna be root 2 over 2, which is again a point on the unit circle. Because this r here is the radius 1. So it's kind of matching, right? It's confirming everything we've been doing. But the second one, the third point, C, is different now. Now we're not on the unit circle anymore. So let's take a look at this one. So here x is going to be, here's your r, here's your theta. So now it's going to be negative 2 times cosine of pi over 4. So negative 2 cosine of pi over 4, you guys said is root 2 over 2. So what happens to the 2's here? They cancel. So you end up with a negative root 2. Negative root 2, yeah. And then your y will be negative 2, because that's your r. But now it's sine of pi over 4, which is again also root 2 over 2, right? So negative 2 times positive root 2 over 2, same thing, 2's cancel. Yeah, so the same thing, so negative root 2. So now you're not on the unit circle, but now you know a point has to have coordinates negative root 2 and negative root 2. Let me check something really fast. What did we say this was? 2. Yeah, I was hoping it would let me plug in polar points on the. Okay, but it's not. Okay. Yeah, question. Logan and then Ken.
So the question is, when I was practicing this, I was just using a document that wasn't doing special rules. More on the side would require us to put in the unit circle values or the actual values.
Let's do one where there isn't a special angle to answer that question. Yeah. So let's here. I run out of room. Let me go here. Let's say you had a point. Let's call this point B. And it was 354 degrees. Let's even change it to degrees. Okay, and you wanted to find, this is your R still. And then this is your theta. It's a little easier to see that's in polar coordinates because you see the degree symbol there, where in radians, it's just a number. But this is polar. So we would do the same thing. X is gonna be R times cosine of 54 degrees. So yes, that's what you would use in calculator in the agreement. Okay, someone help me here.
Yeah.
What's cosine of 54 in degree mode? Let's see, 45 is here, right?
So,
So it should be 0.5, 0.587 times 3,
1.76.
1.76, let's say, okay? And then the y coordinate will be 3 times sine of that same angle. You need to sine as well.
Yeah.
And this is rounded,
Times 352.42.
2.42.
Mhm.
All right, so this point D in rectangular coordinates is approximately 1.76 and 2.42. Was that your question, Tiffany? Or
No,
was it different?
I was wondering, so with these two over here with B and C, then they both have the pi over 4. And so would we always assume that both X and Y are gonna be the same when we have the theta as pi over 4?
Correct. Yeah, yeah. Because if I go here, right? If I ignore the R, cosine of pi over 4 and sine of pi over 4 are the same √2/2. So X will always just be R times √2/2. And Y will be the same thing, R √2/2. So yes.
Okay, so that's why for the ones that have one, it's points that are on the thing graph, but if it's.
On the unit circle,
Yeah, but if it's on the tour, it doesn't go back.
they're farther away, correct. Yeah, these 2 points. 1, 2, 3, 1, 2, 3. If I draw the unit circle. This point was at 2 pi over 3, so it was located somewhere here. And this point here was located right there. Okay. Well, at this point, √2, I think, is like, God, what's square root of 2? Like 1.4-ish something. So then that's gonna be like 1.4-ish here. This is 1, 2, 1.4-ish, 1.4-ish. It's gonna be somewhere here. It's gonna be somewhere here, which is outside of the units. Yeah. This is A, B, C. And then this point is 1.7, 1.8-ish to 2 point something. So it's like located somewhere over here. Yeah. And notice, does that make sense? 54 degrees. Stretch 3 units away. Yeah. Right? Okay. Converting from here to here is a little trickier. It's less straightforward than this. So let's do that and then we'll take a break. Do that real quick. But I want to leave these conversion equations here. All right, let's do that real quick. You guys look beat. Look beat. Let's see, let's just convert to polar now. To polar coordinate. And we'll just do 2 points. We're gonna do the point 2, 1. And then we're gonna do the point -2. And then just for visual, visually, I'm just gonna plot them. So we can kind of estimate, you know, the angle and the value of R. There's 2, -2, there's 1. So +2, 1. Right now, these are in rectangular, because they're asking us to convert. So this is XY, this is XY. So 2, 1 is right here. Here's A. And then B is right here, -2, 1. Okay. What can we say about the angle for theta? What kind of angle should we have? Maybe 30 degrees. We don't know the exact angle. But it's gonna be a small angle. Yeah, a small acute angle. Bigger than 45 degrees or smaller than 45? It's gonna be 45 degrees is smack in the middle, right? So smaller than 45 degrees. And then R, if this is 2 units away, R would be around
A little bit bigger than 2.
possibly a little bit bigger than 2. Right? So let's take a look. Let's just confirm all that. So we're given points in X, Y. We're gonna convert to theta here. Let's start by finding, what do you guys want to find first?
Do the X squared is 5.
You want to do this one first?
Yes.
Okay. All right, so let's see. So X here is 2. Let me just write the equation above. X squared is 2 squared plus 1 squared is going to be R squared. So that turns out to be 4 plus 1 is R squared. So that's 5 is R squared. So then what do we do?
Both sides.
Square root both sides, and then here you gotta be careful. You square root both sides, plus or minus √5 is equal to R. So then you're gonna choose in a bit what R should be depending on the angle that you're gonna use. But you know it's gonna be either a positive √5 or a negative. If you put √5 in the calculator, what is that? 2.23, so we guessed it right? It's just a little bit bigger than 2, which is making sense. Someone had a question. Is it Eric? It just depends on the angle for theta. If we end up with an angle that's like negative down here, then we would want to use a negative R. We'll see. Let's look at what the theta will be. Yeah, most likely it might end up being a positive, but now let's see. So we're gonna keep this for now. Let's see what happens. And then for theta, we're gonna use tangent of theta is equal to y over x. So that's tangent of theta is equal to 1/2. The unit circle might not be able to help you with this one. Because that's tangent, right? Not sine or cosine. So we're gonna use our inverse tangent to help us out here. So theta is gonna be something, gonna be inverse tangent of 1/2. Let's do it so that we get it in degrees, since that way it's a little bit easier to kind of calculate. So can you guys help me here in degrees? Your calculator in degrees, what's tan inverse? 26.
26.565.
26.56, so let's say 26.6 degrees. And so again, we were right. It's a small angle that's less than 45 degrees. And it's positive, right?
Yeah.
So if it rotates positive, what kind of R do we want? A positive or a negative R? Positive R. So then for this point, we're gonna want to use R being positive √5 and theta being 26.6 degrees. This is the polar coordinate for that point. Okay. Let me have you guys do B. Try B on your own. See what you get. But still with positive 26.6?
Oh, I see.
Yeah, careful.
That's I have a question.
Mhm.
This might be a dumb question. So my square root is becomes 12, right? So then this would just. Okay, okay, because I just wanted to. Thank you.
So this angle is pointing this way, right? So do you want to point so that direction? So you want actually. So you actually. Oh, it's also minus.
Yes, 30 degrees. That's that way.
It's negative.
All right, guys, I'm seeing a lot of different answers, all correct. So some people basically went and they just said, I'm gonna do the same thing I did here. And if you do the same thing that you did here, you still get plus or minus √5 is equal to R. Right, because this -2 squared is still just 4. And if you took this route, then you would get theta is gonna be tan inverse of -1/2, but that gives you a different angle. What angle did you end up getting? Negative, because remember, inverse tangent only goes from -90 to +90. So only in quadrant 1 and quadrant 4 are the angle. It's going to give you -26.6 degrees. So in that case, -26.6 degrees is directly opposite of that. So you want your R to be negative, so it shoots backwards. So in that case, if you do this, you would get this point, -√5, and then -26.6. That would work. What I saw other people do is they said, okay, because of the symmetry of this, I know that this was 26.6 degrees, right? This one. So then they said, this is also 26.6 degrees. So they did 180 minus that, which was, God, what did you do when you got that? 180 minus 26.6. 153.4. You made that up? I'll go with it. Is that what you did? Yeah, right. Okay. But if I use that positive angle, that means that now I've rotated in the positive direction here. So what kind of R do I want? A positive √5 or a negative? Positive, so it shoots towards the angle, right? So if I do that, then I'm gonna want to use positive √5 and then 153.4 degrees. That would also work. Yeah. But that's only because of the symmetry that you were able to do that, right? Yeah.
So for the first one, can you also do, instead of -26.6, can you just do 330.4?
So it sounds like what you did, here's -26.6. So did you do 360 minus that?
Yeah, 360 minus 26.
360 minus that would give you, what did you get?
333.4.
333.4. So if you did that. That angle now is going like this. should R be positive or negative? Negative, so it shoots backwards. So then you would want negative 5. So this would also work. Yeah, it's kind of like the sheet that I gave you guys. Right? Here, both of these are negative. Here, both of these are positive. Here, R is negative and theta. So there's still one more. Yeah. Okay, let's take a break though. You guys need some energy. If I had candy to pass out or something. All right, guys, here's some snacks. But let's take a break. Come back at 2:14. You are. Yeah, you got about an hour left. Let's keep going. Okay, so we did polar coordinates. We did converting points, right? We learned how to convert points. So now what we're gonna do is work with equations. So it's gonna get very algebraic. Okay. And so let me show you guys here on Desmos, kind of what we're gonna do. Today I'm gonna show you guys just the equations with their graphs, but we're not gonna graph today. That's what we're gonna do when we come back. Okay. So let's go off of what we know about graphs with equations. So here's an equation. By now you've seen this so many times that hopefully you have a picture of its graph. Okay, it's going to be the parabola. But remember, the parabola is a curve made up of an infinite number of points. And what's true about all those points on the parabola in relationship to the equation of it? What must be true about the coordinates of this point that lies in the parabola in terms of the equation y equals x squared?
The y is squared.
The y squared. Let me change the equation. Let's put 5 minus 3x. No, not quite. All these points are called solution points. But why are they called solution points?
When you plug them in
They're all these coordinates. When I plug in the x coordinate into the equation for x, and when you plug in the y coordinate into the equation for y, you're going to get equality on both sides. Okay, so that's it's kind of magical. Okay, like you're asking what are all the points that when you plug in the x coordinates will also be equal to the y coordinate, all the possible points. And they have a pattern. The pattern is they form the shape of a graph. Okay, that's the beauty. So we're going to have equations with r's and thetas. And so we're going to ask ourselves, like let's say I did r equals 3 cosine of theta. And I get this beautiful circle. Okay. But what does that mean? That means that you think of the points on the circle as polar coordinate points. And they have each point, for example, here, ignore the coordinates. Oh, it doesn't even let me do it. But there's a particular point here that has a certain r distance and a certain angle. So that when I plug in that r distance and I plug in that angle into this equation, it'll satisfy the equation. So just the way that you guys learn graphs about equations in rectangular coordinates, the same is true. Okay. How far is this point from the origin? 3. So what is r of this point? 3.
1.5.
Well, r is how far the point is from the origin. So it's 3 units away. It could be different. Yeah, like here, this point, let's say that's even closer right here. Is this 3 units away? Hell no, it's smaller, right? So in that case, the r would be different. We're going to investigate. That's what we're going to do on Monday of next week. But right now, I just want to show you guys like this point. Give me the polar coordinates of this point right here, where my mouse is at. What are the polar coordinates of that point? 3
0.
3 comma 0, because theta is 0 there, right? So I plug in 3 for r and plug in 0 for theta. What's cosine of 0? 1 times 3, 3, which is equal to r. See what I'm saying? Versus if anyway, I'll take it that far. We're gonna do more graphing on Monday. Okay, but that's kind of the idea. But the thing is, some equations look nicer in one form than they look in the other form. So for example, here is the equation of a nice circle of radius 5 that you've probably learned in the past. X squared plus y squared equals the radius squared, which in this case is 5. Okay. Here's another one. This is an equation with this graph in rectangular coordinates. We're going to learn how to turn this equation into a polar equation. Okay. Here's another one. It's like a circle with a butt. Okay. It's like it's twisting in itself like that. It actually has a name. It's called, I think, a cardioid.
Yeah.
Okay. Circle with a butt's funny. So these all have points that satisfy, rectangular points that satisfy this very complicated equation. So that's very complicated. And if I wanted to do anything with it, like any kind of manipulations, it looks pretty nasty. So what we're going to do is say, how can I convert this into r's and thetas where it might look nicer so that I can do my algebra a little bit better. Okay. Cool. Okay. So what we're going to do is not focus on the graphs right now. We're just going to focus on how do I convert these equations into polar equations so that r's and thetas are used instead of x's and y's. So let's see how we're going to do that. Okay. So just the way we use these conversion equations, we're going to use them again, but now more algebraic. Okay. So actually, I'm going to erase this. We're going to need some room. Okay. And then just to help you visually, I'm just going to write those conversion equations here. They're not going to show up on the video. So we got r cosine theta, y equals r sine theta. And then we have tangent theta is y over x. And x squared plus y squared is equal to r. Just for reference. Okay. So to convert equations from polar to rectangular form, or vice versa, we'll still use the same conversion equations that we did before. Conversion equation that I wrote over there on the board. And so let's start with the ones that I showed you guys on Desmond. The homework will say convert to polar form. And let's do the first one, which is the circle of radius 5. This guy here. Okay. It's kind of like identities, where you were using identities to substitute them in your equation, right? So which of these 4 do you see on that equation? Fourth one, right? So x squared plus y squared, I'm going to now rewrite it as, what is this supposed to equal? R squared. So just the way you did an identity, right? You rewrote this with what it equals. So this, I can rewrite it as r squared equals 25. You know? I'm using the identity x squared plus y squared equals r squared and just rewrite it. But I did that because now I have an equation that was in x's and y's to now only r's and thetas, possibly not thetas, but at least in r. Okay, and I'm trying to find r here, so bless you. Go to both sides, and then r is gonna be plus or minus 5. But we want only one of them. So let's see, let me just draw the little circles here. Here we have radius 5. If r is positive 5, our ray at angle 0 is stretching here, right? It is r at positive 5. Does this equation use any thetas? No, but look, that's okay, because no matter what theta I choose, those points are always 5 units away from the origin. Can you see that? Yeah. Right, so it's like your arrow is always gonna be 5 units long, and no matter where I rotate it, it's always gonna include points on the circle, because they're all 5 units away from the origin. What if I chose r is negative 5?
That's good.
At angle 0, I'm now shooting it backwards, though, right? So depending on my angle theta, my point is just going backwards. But that's still gonna work, because that will still be 5 units. Okay? So both of them are correct, actually. But we usually go with the positive r, since they both work in this case.
Is it kind of like absolute value?
Kind of, yeah, kind of, in this case. Yeah, so both will work, though, okay, but usually we choose r to be positive, because it's less confusing with that whole backwards business. So this equation, look at that. What's easier algebraic wise, that one or this one? Hella easy. So this is how you represent the equation of a circle centered at the origin of radius 5. It's just the equation r equals 5. Because all these points, what's true about all these points in polar coordinates? What do they all have in common?
The radius is not-
R is always 5, which is exactly what this is. It doesn't matter on the theta. Okay. All right, let's do the other one that was a little nastier. X squared plus y squared plus 3x equals 3 times the square root of x squared plus y squared. Look it up on that sheet. Just a bit, right? All right, so you're gonna start here. I want to convert it into polar. So I want to be able to use these conversion equations as much as I can to get rid of all the x's and all the y's. Okay, I know. Told you. It's getting nasty. Okay. So can we use this guy again?
Yeah.
R squared? Yeah, anytime I see an x squared plus y squared, boom, r squared can be replaced with that. So this is gonna be r squared. What about this one here? What can we do?
R cosine is there.
X can always then just be replaced with r cosine of theta. So I can rewrite this. Plus 3 r cosine of theta. Okay? Equals 3. Look, I see another x squared plus y squared. So I can rewrite this as the square root of r squared. Here's where you gotta be careful. Was the square root applied? Did you apply it yourself, or was it already part of the equation? So you don't consider plus and it's just gonna be the positive r. Okay, so it's just gonna be r squared plus 3r cosine theta, and that's just gonna cancel 2 and r. Only when you apply the square roots that you gotta consider. All right, any ideas? If I divide by 3, it'll cancel this 3, this 3, this 3, and then not here.
To divide by r.
You could divide by r, you can, Okay, but remember I told you guys, try to, when you're doing an equation, avoid dividing by variables. Because R being 0 gets funky, and I'll show you how that's gonna show up. I could try to factor instead, but to do that, let me bring all the terms to one side.
Subtract three,
Subtract the 3R.
yeah,
Yeah, so subtract the 3R. So then I'm gonna end up with R squared plus 3R cosine theta minus 3R. And everything has an R. So factor it out, factor it out. And let me go slow here. That's gonna turn into a R. This R is gone and that R is gone. Cosine theta minus 3. And I factored this times this whole thing equals 0. So what do we do algebraically when you factor two things that multiply to 0?
You separate them.
You separate them each equaling 0. Beautiful.
Second.
Like orchestra right now. That was fucking awesome. All right, so either R will equal 0 or R plus 3 cosine theta minus 3 is equal to 0. Most of the time in these equations, you're gonna want to write the R by itself. You'll see on Monday why. Okay, so we try to usually isolate R if possible, if it's not too complicated. So how can I get R by itself?
Add three to both sides
Add the 3
and divide.
and subtract that sucker, yeah, so add the 3 and then minusing the 3 cosine theta. Cool. Okay, let me explain what do I do with this? That's weird. But with the algebra though, before I show you guys the graph stuff. Any questions from here to here? Cool. Okay, so let me show you what's happening. Let me leave this. Okay, perfect. So let me show you that real quick. If you want to factor the 3. You don't have to factor the 3, no. So let me go like this so it shows. Oh, okay, perfect. All right, so watch. Let me ignore this guy over here. Oh no. Okay, that nasty rectangular equation is this cardioid here, right? But now I'm gonna write the R equals 3 minus 3 cosine theta, so that Desmos reads it as a polar equation. And look, it's the exact same graph. But now these points, you're not thinking them as XY points, you're thinking them as R theta points. Okay, R theta points. And so when theta is pi, what will R equal? What's cosine of pi? -1. -1 times -3. 3 plus 3? 6. So when theta is pi, R is 6, which is the point right there on the graph. Okay, so you're thinking of this graph as now points of R theta. Okay, so this coincides with the original graph. But what about this one? What about the R equals 0? What's the graph of R equals 0? Let me see if you guys can see the red point. You see that little ass red point? Think about it. On polar coordinates, if R is 0, how far is it from the origin? It's always the origin. It doesn't matter the angle, it's just always the origin.
Is it even a circle at that point?
It's a circle radius 0, sure. Because it's the point, yeah. Yeah. We're gonna see that, yeah, we're gonna see that. But basically, what this is saying is that this graph, this original graph, is this big cardioid graph that also includes the origin. So on this nastier graph with x's and y's, if I plug in the origin and x's and y's, that's 0, 0, right? So I plug in all zeros for x's and y's, and notice I get 0 equals 0. Right? For both of these, For this one, that's kind of what it's saying. Like, the origin is also included on this graph. And the cardioid, but they both really just paint the same picture anyway. Does that kind of convince you guys with it? Okay. My teacher never explained that. So I was so fucking lost when that happened. But yes, so that's what it's saying. This is saying that this is the graph of the cardioid overlapping with just the origin point, which is already part of the graph anyway. Okay? You have, this week you don't have a problem set.
Oh my God.
Okay, so let me have you guys try one. You guys can do it. Just take it step by step.
We
Practice.
appreciate the offer. Where we gracefully decline.
Convert to polar. All right, so you got x squared. X squared plus y squared equals 9y squared. 9y squared, yes.
Oh my God, it's killing.
Try it out. Remember, when you use your conversions, you do not want to see any more x's or y's, only r's and thetas, okay? So try to think, well, how can I use these to convert so I only end up with r's and thetas? That's your goal. And then do a little algebra.
Do we still have markers?
You guys are like my kids when I take a road trip. They're like, are we there yet? And then I tell them, does it look like we've approached the end? So we're gonna do the opposite,
Okay.
convert to rectangle, and then we're done. Try that. Try that.
Wait, okay, this one I'm not gonna do. No. Do we keep the square?
You do keep the square. You do. That square is gonna make it a little nastier than
That's
And you want
square.
it.
Can I use square cosine theta?
correct.
Okay.
Correct.
Well, I'm guessing that's the first one. Thank you.
Yep. Guys, if I square the x here. If I square this thing here, is it just the r being squared? No, the r squared and the cosine is gonna be squared as well. Okay, so be careful. When I got evaluated by students, part of the comments were provide harder examples in class.
No, people said that.
So that they match like the exam, because my examples were too easy and the homework were really hard. And they didn't meet that. So almost there. We have an- Well, here is our score.
I was dumb. All right. Oh, really? We can both turn that in.
There's nothing. The only thing, which of these only uses a y and not an x? Out of these three here.
I give up.
The one that only has a y but no x's on it. There's an x on it. Exactly. So you're gonna rewrite the y with r sine theta.
So it would be like 9 r. So you plug in r sine.
It's coming wrong. No, so this 9 stays here. this line would stay there. But the Y that's being squared
So now it's R, this.
are sine theta. Because the Y is R sine.
And then from there, whatever is the nine of the square two now, or is it one?
The 9 would stay. The 9 just tags along. And similar thing for here, for this one.
God, it's sorry. So there's a.
Yeah, instead of, or it's gonna be, see how this is the only equation that has an X and no Y's on it? So now the X, just the way you replace the Y, the X is gonna be replaced with R cosine theta.
This one's.
At some point, Benji might show up, yeah, good intuition. Rohan, you had a question?
Yeah. It's two different plus minus, so that's like an issue. I've heard next one.
There he is.
I divided the x squared and since the y was on top of the x. Yes. I just used
Beta.
I forgot what it was to divide variables, but I ended up on that side, and then I had like 9, 10 theta. So,
R squared.
No, I need to.
Well, just be careful with dividing by R's. Here, instead of dividing by R, we moved everything to one side factor. Try doing that.
I did it for.
Instead of dividing by R squared sine squared. Try instead subtracting this to this side.
But I can.
Yeah, like here, right? If I wanted to move the 9y squared to this side, I would just subtract it.
Oh.
So it's kind of like that. Also here when you square R. Sorry, here when you square that, both, that should be R squared. You got it? Okay.
Okay,
My instinct is show me the facts. Like, I feel like
it's like.
Some combine things a little bit more before you have to factor. Yeah, you have to combine things a little bit.
Yeah.
Or square right now. Just.
That's what I just did. That's not the way.
oh, but okay, then I'm away. But it has.
And you already have. Already have.
When I'm pulling the R out. It's not hard. It's just minus one. Pull the R out, you still negative 1. If it's 9 by. Added to 0. That's what I.
Plus or minus.
So I just go 1. Well, it does.
Negative?
I'm not sure.
Oh, so this is the one.
Oh, yeah, kind of moved it.
This, but then the cosine. Because I can't do this. Oh.
Why did you separate? Why did that?
There'll be another on.
Well, let me see.
You don't want to serve. I don't want to serve. I mean, I don't know. But you might.
I got the website to the website. Then you have everything still on the website. Exactly. Negative and also.
That makes sense.
Change. Just. You're right. M squared plus Y squared. I mean, I can show you what I did, but. Then I know that Y squared. Oh, I can't. 9, 10, 15 squared. Yeah, that I changed. I did the other.
All right, guys, real quick. Let me change something a little bit that might help. Okay, let me change something a little bit. Okay. Take it or leave it. You don't have to take it, but a lot of you really want to divide that R. Yeah, you really want to divide that R, which is fine. So let me redo this problem over here. Let me redo that problem, and let's say I do this problem and I'm up to this step. I'm up to this step. Like this, and I really want to divide that R, okay? You just gotta be careful. Before you divide that R, if R is 0, the origin's included. If R is 0, the origin has to be included, okay? So then you just have to make sure that this equation includes the point 0, 0. If it includes the point 0, 0, then you're fine. You can divide that by R because you can assume R won't be 0. Because this guy is going to include the origin as well. I'm gonna say that again, right? For me to divide by R, I have to assume R is not 0, right? Which would have given me this equation. But this graph, as we saw, also included the origin. So it still also includes this guy. You get what I'm saying? So if I divide by R, I just have to confirm that the original equation includes the origin. If it includes the origin, then you can divide by R. That's fine because the resulting graph will still include the origin. But if it doesn't include the origin, that's where it can get funky. Is that cool? So this one, does it include the origin?
If you multiply everything by 0, or if you plug in the numbers, or if everything's being multiplied by your variables, it's gonna include 0, 0.
Yeah, right. If I plug in 0 for X, 0 for Y, I'm gonna get 0 equals 0. But let's say I change the equation so they look like that. Does it include the origin? It would not. So that's where you got to be careful by dividing by R's. Okay. All right, Rohan. Yeah. You want me to check? All right, hold on. We're gonna work it out together. Is that okay? So the original equation includes the origin. So let's just put this little fact here. So if 0, 0 is on the XY equation, it's okay to divide by R. Because the ending result will include the origin. So that means that I could have done this equation a different way. I could have divided everything by R. And I get R equals 3 cosine theta 3. And then I minus this to this side, and then I get that final result. It is easy. I know the temptation for what you would do. Yeah, it's just, there's a little bit of like theory there that's hiding. Okay, now we do this one. It's confirmed, 0, 0 is included in the origin, so it's okay to divide by R. Okay, so let's see. Let me start this all over again. So X, you guys replaced it with R cosine theta, right? So I'm gonna go step by step. So this is R cosine theta. That is being squared. This you replaced it with just R squared. And then here, the 9 is just the 9, but it's the Y that you're replacing. That replaced with R sine theta. That whole thing squared. So here's where you guys have to be careful. If I square this whole thing, both the R and the cosine are squared. So you need to write it like this. Like that. And then this is just times R squared. 9 R squared sine squared of theta. Cool? Okay, the origin is included, so it's okay to divide by R's. Okay. Let me multiply this a little bit out. Hold on. R squared times R squared. R to the 4th cosine squared theta. Okay. Simplified it. And now what you guys really want to do is divide by R, but I can divide even by bigger R's. I can divide by R squared, right? Because that might as well divide not just by one R, but the product of 2 R's. So then that will cancel with this one, that will cancel with this guy. So you end up with R squared equals cosine squared theta, 9 sine squared theta. And then, like I said, usually you want to get R by itself. So then we're going to divide by cosine squared theta, divided by cosine squared theta.
Isn't it divided by a variable then?
Let's see, so
Maybe that is square.
if theta is yeah, it is. So if theta is pi over 2, for example, then we can't do this, right? So by doing this, we're excluding all the polar points of pi over 2 and 3 pi's over 2. Yeah. Let's see the final result, what that would be. So we would get R squared. Yeah, that's a good point. Sine divided by cosine.
You make that tan.
You can make a tangent. Yep, that's tangent. Which is going to be undefined at pi over 2 and 3 pi over 2. So it's still kind of a green. Yeah. And then what did you guys do from here? Square rooted both sides. Then you end up with plus or minus, but we're going to go with the positive because they will both work. 3 tangent of theta. Is that where you guys were, I think, most walking around? It would be plus or minus. Oh, I erased it. But like earlier we had plus or minus 5. The minus will also work. Yeah. It'll just point everything backwards. So when you guys get up to here, technically, you could have also stopped here. Because that's an equation in polar coordinates. Okay, it's just the textbook likes to isolate for R. But this is technically also work. Here you do include the points, polar points with pi's over 2 and negative pi over 2. Question, yeah.
Could you have square rooted as soon as on
Like-
the first step or?
Oh, that's it. Yeah, yeah, you could have. Like the square root, all this stuff off?
Yeah.
Yeah, and you would end up with. Yeah, it would have also worked, yeah. That would have worked this way. Cool. Okay. All right, that's converting to polar. 2 examples and then we're done. We gotta convert into rectangular because the algebra is gonna be a little different. Okay, take a look. That was the nasty one there. Yeah, just 2 examples. Let's see how we're gonna do this. So here we're gonna convert to rectangular. And let's start with an equation in polar form. So it would be r cosine theta plus 2 sine theta. Well, you know how right now we were going kind of, we were using the left side to convert them to the right hand side.
Now we're gonna use the.
Now you kind of want to feel, now you kind of want to go the opposite way.
Use the left.
Yeah, so now you want to see how can I convert something like this to just an X,
Okay.
okay? Do we have any r cosine thetas here?
No.
Any r sine thetas? Any r squares? No. Right. We want those because r square shows up here and then these are here, right? So what we're gonna do is do a little algebra. I can multiply both sides by something to make that happen. What can we multiply by? By r. I multiply by r on the left-hand side, and then I multiply all of this by r as well. Okay? That's tricky. Because unlike these ones, everything was there, you kind of just have to like substitute. Here, you don't do that. You have to creatively know to multiply them to make it happen. So that r gets distributed here, and it gets distributed here because you're adding, right? So then this becomes, what does the left-hand side become? R squared. This becomes
R cosine.
cosine theta, and then 2 sine theta. Now I have what I want, right? I'm using my conversion equation. This turns into this turns into a x
Plus 1.
plus 2, exactly, and this is just a y hiding there. And that's it, you're done. Okay. If you were to graph this on Desmos and this on Desmos, you would get the same graph. Questions?
Could you get a parabola with the degrees and?
Like polar?
Yeah.
Let's do that one third. We'll do that one third. Yes, you can. You can. Well, I guess. Like that, right? The y would turn into
R sine theta.
r sine theta. And then x would be turned into, there it is. So, like I said, sometimes rectangular forms are way nicer than polar forms. Or sometimes polar forms are nicer than rectangular forms. So that's why you're learning this skill, because down the line, you're gonna want to change it to your advantage. So that you can do the math and the derivatives and all that stuff you're gonna learn. Easier than doing it to this monster. Okay. Okay. The last example, let's take a look at this one. Let's put it side by side. Last one here we have is. Oh, yeah. Okay. 2 theta there. Okay. Do any of these conversions use two thetas? No, so what do you think we wanna do?
Square times of.
Use that standard.
Use an identity, use an identity. You guys, I tested you on double angle identity.
Use the one subject was.
Two signs.
Cosine.
Correct. So you still have to use all that, okay? Okay, let's see. Now, I used an identity, but I haven't done any conversion yet. I just did trig identities. But now I want to see if I can use this now to convert. So when we started this one, what did we want in front of the cosines and sines? R's, right?
So
We still want that so that I can convert them to x's and y.
So you-
But- Here, these two are adding.
And those are.
So by multiplying by r, you distribute. So here, I want to multiply an r here and here, but are these adding?
No.
No. So how many r's do I want to multiply the right-hand side? I want to multiply by 2. So here, I'm for real. So you're gonna want to multiply by r squared. And let me show you why. Whatever I do on the left-hand side, right-hand side, I have to do it this side. So the left side, because of that, turns into an r cube. Here, let me move this down. So you guys can see it's tricky. If you're not seeing it, it's tricky to see it. So I'm gonna literally multiply everything out. So it's 2 times sine theta times cosine theta times r. And so what we're gonna do is rearrange those r's to our advantage. I'm gonna move this r here. So this becomes 2 times r times sine of theta. And then move this r in front of the cosine. So that it looks like that. You guys see that? All the little, and the textbook will go here and, but just go to the next step. Which is tricky. Am I distributing it? No, because you're not adding. It's not distribution. It's different. It's manipulation of product. Okay? So then this becomes r cubed equals 2r sine theta. And then that other r cosine theta. Cool. But then we're in a pickle for a little bit, yeah.
Question on the blue, why are we able to multiply the all both sides? In order to get the equation.
We're allowed to multiply the r to both sides, because for whenever you're solving an equation, as long as you multiply both sides of the equation by the same number, they're still equal to one another, and r is an unknown number. So it's still technically the same number. Yeah, that's right. Okay.
You just go to 2xy at that point?
Well, look, this becomes y, this becomes x, but then we're stuck with the r cubed.
Just make it like x squared plus y squared times square root x squared plus y squared.
Mhm.
You know what I mean?
Oh, you take one out, you take an R squared out and then you make the back into.
Okay, if I was to do that, that would become the r squared, and then what would that become?
Square root x plus y.
That would become plus or minus square root of that. Okay? But you're gonna end up with plus or minus here in this case. So I think this is what you guys are saying. You're saying split this up like that, right? Okay, so then this becomes what? X squared plus y squared. But that r, if I wanted to get this r by itself, you guys are saying square rooting it? Plus or minus, but we're gonna go with the positive one. We'll confirm that in decimal. Let's see. Let's say, so you guys are saying turning it into that, right? Okay,
Yeah.
no, so when I square root two numbers like that, it is not equal to that. What's the square root of 4? What's the square root of 9? What's 2 plus 3? Okay, what's 4 plus 9? 4 plus 9. 13? Is that the square root of, is that equal to 5? No, these two things are not. So you can't just do this. That's called the freshman's theorem. Because it's like wishful. Yeah, so you have to leave it like that. There's nothing to do. Okay? All right, and then you guys are saying this becomes y, and then that becomes x. Technically, this is plus or minus. Let me see. Weber sign will not do it that way, okay? They don't like the pluses or minuses there. Let's say it's plus. Let me show you. It's not gonna work. Not gonna work. No, it's not gonna work. Let me show you guys why. I'm sorry. In this case, I'm the messenger, so don't hate me. Watch. So we had R equals cosine theta plus 2 sine theta. Is that correct? Oh, maybe it will work. Okay, let's see. Now I'm gonna put that disgusting thing we got. So it was the square root of x squared plus y squared times x squared y squared equals 2xy. Two. Oh, I'm looking at the wrong one. The original one was sine of 2 theta. Oh yeah, it's not gonna work. That's called, yeah. So look, when I graph that, look, when I graph the positive, it only gives me half of it. But if I do the minus, it gives me the other one. Plus or minus would work, but Weber sign, and normally you don't want an equation with pluses or minuses. Let me put the plus or minus there. Let me see, does it let me do that? No, it won't, but. So let's see, I think we'll be fine. So what we could do, let's see. What we could do. So we can't do this because we don't end up with the original graph of the original. So maybe what we could do is square both sides. And when I square this, it gets rid of the plus or minus, and then I'll get rid of the square, right? So then this just becomes, what happens when you square this, guys? It's just, yeah, the square root goes away and the pluses or minuses are gonna become positive. But then I also square this guy. Is that okay? And what happens when I square these? Like that. So this is just this square. This is this times this in itself, right? So then that's just gonna be x squared plus y squared to the power of x squared times another copy of it is just the power of 3. Okay, I think that will work. I think that one will work. Let's see. So it was x squared plus y squared to the 3rd power equals 4x squared y squared. Bam! That'll work. Okay? So moral of the story, if you end up with a plus or minus, at the end just square it and cross your finger. That the algebra doesn't get discussed. Yeah.
We could just recognize that it would just be that function or not.
The equation. It would be, yeah, it would just be cubed. Correct.
Would it not have been reversed because square from the R cube?
So, hold on. Yeah, and that's what I did on that. So, on the notes, just so that you guys don't get lost, you see how we had to cube? How we had to cube this? So what I did on my notes on the PDF, the way I did it is this equation uses an r squared, right? So if I can raise my r into an even power, I can manipulate that into an r squared. So let me show you. So if I would have squared both sides from here, you would have ended up with what's r cubed to the power of 2? R to the 6th, and then this would have been 4 R2 times another R2. I would have squared this, squared this, squared this, squared that. R to the 4. And then. Cosine squared. I'll just leave it like this, look. R squared cosine squared. R squared sine squared. I'll leave it like that, okay? So the r to the 6th, I can rewrite this r to the 6th as r cubed squared. R squared cubed. Right? Because multiplication, these multiply, so then I can swap them. And now this becomes an r squared, which becomes that. And then the r squared cosine squared is the x squared. And the r squared sine squared is the y. You see that? So if you have an odd power of r, you can square both sides. You know, just be careful. And do this little conversion. Okay? Roll. You still want me to check? Okay. All right, guys, we're good for today. All in here. Okay. Algebra will be nasty at the end of the homework. Oh, shoot. Yeah, I'll leave it so you guys can see the work. Okay, let me check your ways.